Hey everyone. So in this video I'd like to talk about graphs of inverse functions. So we defined this idea of an inverse function in the previous video. We said that if f takes some input value, let's say a, to an output value of b, well, in the inverse function just reverses that. It reverses the actions of f, and it takes an input value of b back to an output value of a. And so what this is really saying, if we're going to try and talk about the graphs of inverse functions, is that the point a comma b is on the graph of f. And the fact that f inverse of b leads to a is saying that, well, the point, not a comma b, but b comma a is on the graph of f inverse of x. And so really the relationship between the graphs of, or the points on the graphs of these two functions is that the points have their coordinates switched. Right? A comma b is on the graph of f, and b comma a is on the graph of f inverse. And so really I can think of the graph of f inverse as just taking all the points on the graph of f and swapping their coordinates, their x and y coordinates. And so if we understand what this does to the graph of a function, then we can really quickly graph inverse functions. And so here, this isn't an example of a function, this little smiley face on the right, but I think it'll help us make sense of what it looks like to swap the coordinates of some points. And so here, let me encourage you to pause the video and take this smiley face graph, take all of the points and swap their coordinates and see what's the resulting picture you get out. So here, let's go ahead and do this together. So let's start with the mouth. So here, let's take these 3 points and swap their coordinates. So here, this last point on the right, it's the point 4, 1. Right? An input coordinate, an x coordinate of 4, an output coordinate of 1. And if we swap those like an inverse function would do to the point 1, 4, this point would end up out here at 1, 4. And similarly, if I take this bottom part of the mouth, the point 3, 0, and if I swap the coordinates, I would get 0, 3, this point here. And then lastly, I would take this coordinate, or this point 2, 1, swap its coordinates and get 1, 2. So the mouth, after swapping the coordinates of all the points on the mouth, really would look something like this. Okay, what about the winky eye? We have this winky eye here. Well, really that's associated with this point 4, 2. And if we swap the coordinates of that point, we get 2, 4. Right? And so if we make sure that we still have that part of the graph that's kind of winking, it looks something like this. And then lastly, we have this point 2, 2. And if we swap the coordinates, we end up with the same point, 2, 2. And so really, this picture that we got, this resulting picture, the smiley face, really was reflected over this diagonal line. And the equation of this line is y is equal to x. Right, so really, this idea of swapping the coordinates of points, the x coordinate and the y coordinate, it's really reflecting those points across this line, y is equal to x. And so if swapping coordinates of points is what an inverse function does, then really the graph of an inverse function is obtained by reflecting the graph of the original function over this diagonal line y is equal to x. In general, the graph of f inverse of x can be obtained by reflecting the graph of f of x over the line y is equal to x. And so let's go ahead and apply this idea to this function g of x is equal to x cubed plus 1. So let's sketch the graph of g of x cubed plus 1 and use this to sketch the graph of g inverse. So g of x cubed plus 1, this takes our x cubed graph and shifts it up 1 unit. And this is x cubed plus 1, that shifts all the points on the x cubed graph up 1 unit. And so our graph looks something like this. Roughly speaking. Right, so this is g of x. And we're saying that the graph of g inverse, well, it's going to be obtained by reflecting all the points of g of x over this line y is equal to x. And so the points on this line y is equal to x, so whatever point this is out here, that's not going to change because reflecting it over this line is going to leave it on this line. But we can kind of see that these points here are going to get reflected over to the point, well, this is the point 1 comma 2, so it gets reflected to the point 2 comma 1. So that's for the g inverse function. The point 0 comma 1 gets reflected at the point 1 comma 0, and the point negative 1 comma 0 gets reflected to the point 0 comma negative 1. It looks like they all fall on a line, but we can see that in between there's some curvature happening. And so here, really the graph of this g of x, or g inverse of x function, well, here on the g function, it kind of skyrockets upwards, so we can kind of picture that it skyrockets to the right on the g inverse function, and looks something like this. All right, so this is g inverse of x. You can see it's just mirrored over this y is equal to x line. And so maybe to add even more context to this picture, we've already talked about how to find the equation of an inverse function. Let's go ahead and find the equation of g inverse of x. All right, so how do we do that? Well, we take our g of x function, and this function tells us how to to take an x-coordinate and find or determine a corresponding y-coordinate. And so maybe I can write it this way: y is equal to x cubed plus 1. And we want to find a rule that will take us from the y-coordinate to an x-coordinate, right, in reverse. And so what do we do? Well, we can solve for x here. So I would subtract 1 from both sides of this equation. So we have y minus 1 is equal to x cubed. And then, how do I get x completely by itself? I don't want a rule telling me what the value of x is going to be from y. Well, I would take the cube root of both sides to undo that cube. And so we get that the cube root of y minus 1 is equal to x. This is a rule that takes outputs of our g function back to inputs. And so this is really the rule for our g inverse function. This is g inverse of x is equal to the cube root of x take away 1. So a few things I want to say about this cube root function here. We haven't really talked about the cube root function so much. Is that, we can see in the graph for g inverse of x that unlike the square root function, it continues out to the left, even taking in values, negative values for our input. And so here, this graph, it's a shifted cube root function, right? Shifted to the right 1 unit, but we can see that it's okay to plug in negative values into this function. Okay, so let's do one last example. Here I want to graph h of x is equal to the square root of x plus 2, and I want to use this to sketch the graph of h inverse of x. So let me encourage you to pause the video and try this example out yourself first. So this h of x function, right, really I can kind of think of it as some transformation of f of x is equal to the square root of x, right? F of x is equal to the square root of x. Well, it's very similar to our h function, but the only difference is that instead of having x under the square root, we have x plus 2. In other words, it kind of looks like we've input x plus 2 into this square root function. Right, that's exactly what h of x is equal to. And so inputting x plus 2 into a square root function, right, adding 2 to the input of our square root function, well, that shifts our graph horizontally, our square root function graph horizontally to the left 2 units. Right, so our h of x function, it looks like our square root graph, but here if I plug in -2, I get 0. If I plug in -1, right, -1 plus 2 is 1, and it gives me the square root of 1 is 1. And then if I plug in 2, I get the square root of 4. And so really here it looks like our square root graph just shifted 2 units to the left. This is h of x. And so if we want to sketch the graph of our h inverse function, we're reflecting this graph over the line y is equal to x, this diagonal line. And so here I can see that, maybe the point -2, 0, that would end up at this point negative, or 0, -2. And -1, 1, that ends up at the point 1, -1. 2, 2 ends up at the point, well, it stays there, 2, 2. The graph of our h inverse function reflected over this line y is equal to x looks something like this, h inverse of x. And so what might be an equation for this graph? It looks kind of familiar, it looks kind of like a parabola, but it only looks like half of a parabola, right? It looks like half of maybe this parabola. And so what would the equation of this parabola be? Well, it kind of looks like the x squared parabola, but shifted down 2 units. Right, so here, h inverse of x, this is the x squared minus 2 parabola, but really only for values that are greater than or equal to 0. We see that the inverse of our h function is only the right half of this parabola. So it's this parabola, but just for x values greater than or equal to 0. Maybe let's dig into this a little bit. So we've said that the inverse function and the original function, well, their inputs and outputs are switched. Right, so the inputs and outputs of a function and its inverse are switched. But then this also would mean that the domain, right, the set of all input values for a function, and the range the set of all output values of a function are switched to. Right, if a function and its inverse switch inputs and outputs, then the domain, the set of all inputs, and the range, the set of all outputs, they're going to be switched between a function and its inverse as well. Right, so here the domain of h of x, well, right, h of x was the square root of x plus 2. We can see the x coordinates of this h of x function only fall between -2 and actually all the way out to positive infinity. These are the numbers I can plug into my function, -2 to infinity. And then the range of h of x, well, if we look back up here, the output values are 0 or greater. Right? The square root function isn't going to give me any negative values. It's not shifted downwards or anything. It's just going to give me values from 0 and above. And so here, the range is from 0 to infinity. And then for the domain of the inverse function, well, we swapped all the x and y coordinates, and so the domain here, we can see it's the right half of the coordinate plane. It's from x is equal to 0 and greater. Right? So here this looks like a domain of 0 to infinity, and then the range, well, again, we can sort of look at it. We can see that it starts the lowest value of -2 and goes upwards on forever, right? So here this has a range of -2 to infinity. And we can see that the domain and the range between these two functions have swapped.